A child places a picnic basket on an outer rim of a merry-go-round that has a radius of 4.6 meters and revolves once every 30 seconds. So that's pretty slow, huh? So what's given to us here? It looks like the radius is given to us, which is good, right? So we know the radius is equal to 4.6 meters. And it revolves around once every 30 seconds. So the period is 30 seconds per one revolution, right? So that's the period. Okay. So those are given to us. We don't know the mass of the picnic table or picnic basket, and that's pretty much it, right? So part A asks, what is the speed of the point on the rim of a merry-go-round? Well, for part A then, since they want speed, v is equal to distance divided by time, right? Therefore, the distance that point travels around one complete circle is a circumference, which is 2 pi r. And the time that completes one revolution is called period. So we can say 2 pi times the radius, which is 4.6, right? Divide that by period of 30 seconds can give us our speed. And our speed at this point comes out to 0.963 meters per second. Okay? So that's part A. And then for part B, how large must the coefficient of static friction between the basket and the merry-go-round be for the basket to stay on the ride? Well, let's do a little free body diagram here. We know the friction is what's keeping this picnic basket from sliding off the circular path, right? Without the friction, it's going to go, right, tangentially. Well, this also has the normal force and Fg acting straight down. Okay? And you know F normal has to equal to Fg, right? So sum of all force in y is equal to MAy, but you know Ay is going to be 0 because it's not going to be going off or through the merry-go-round. And sum of all forces in y, obviously, we have F normal, right? And then we also have Fg. So 0 is equal to, I'm going to consider up direction positive. Therefore, F normal is positive minus Fg. So our F normal is equal to basically Fg, which is mg. Okay? So that's good to know, right? Now let's take a look at sum of all forces in the radial direction, or in the horizontal direction, right? And that is simply MAC. So if I take a look at sum of all forces in the radial direction, that is just frictional force. So MAC is equal to friction, and they are both positives because AC, we're going to always consider the direction of AC to be positive. So since friction is acting in the same direction as AC, friction is this, in this case, is positive. All right. Therefore, mv squared over r is equal to mu times F normal. Well, we know what F normal is. Our F normal is mg. Therefore, it's mu times mg. So notice how the mass of the picnic basket will cancel out. And if we solve for mu, or mu is equal to, then v squared over rg. And that is equal to, we know what v is, which is 0.963 squared over r, 4.6, times g of 9.8. And if you work this out properly, I guess you get 0.021, which is really small, actually. Okay. Alrighty then. Let's take a look at the next problem. A conical pendulum is formed by attaching a 50-gram mass. So it might not be a bad idea to convert this mass into kilograms. So 0.050 kilograms, okay, mass, to 1.2 meter string. So this length of this string right here, right, is equal to 1.2 meters. The mass swings around the horizontal circle with radius of 25 centimeters. So this radius here, r, is equal to 0.25 meters. Well, we could probably calculate this angle theta here because we know these two dimensions. Right? This theta is simply, this is the opposite, this is the hypotenuse, right? So we could probably use sine. So sine of theta is equal to, right, simply r over L. So theta is equal to sine inverse of r, which is 0.25, over L, which is 1.2. So our theta is equal to 12.02 degrees, right? So 12 degrees. All right. So that's good to know. So A, what is the speed of the mass? So they want to know what V is. Okay. To find out what V is, we're probably going to have to find out what this tension is to keep it from going in a circular motion, right? So if I were to take a look at the free body diagram of that ball, right? So here is the tension diagonally, I guess. Right? So here's the tension. And this tension will have its vertical component. Okay, it will have its vertical component this way. It will have Ty. And it will also have Tx. Now I could draw my Tx here, or I could draw my Tx down here. Okay. That Tx the same tx here. Okay? And this angle here is theta, which is 12 degrees. Okay? And of course, I have FG going straight down. And we know our FG is just mg. Okay? Our mg is, well, we can work that out later, I guess. So, to figure out this tension, we could probably work with these two because I could figure this out. And since I could figure this out, I know this is equal to this. And we know the angle here, therefore we can find the tension. Right? So it's probably a good idea to figure out what that tension is. Okay? So let's do that. Okay? So here, Ty, so let's take a look at y direction first. If we take a look at the y direction, sum of all forces in y is equal to MAY. However, in the y direction, this thing is not accelerating up or it's not accelerating down, so my acceleration in y is 0. And sum of all forces in y, there are only two forces, right? That is T sub y and Fg, right? So when I set them equal to each other, 0 is equal to, I'm going to consider the direction up positive, right? That means Ty is positive minus Fg. Okay? So our Ty is equal to Fg, which is equal to mass, which is 0.050 times 9.8. So our Ty is equal to 0.49 newtons. Well, that's fine and dandy, but can we figure out what the T is now? Right? Well, our T is then T times, Ty is also then T times, right, cosine of the angle theta, because it is adjacent component of my T. So my tension T is equal to, right, Ty over cosine of theta, which is 0.49 over cosine of 12 degrees. So if you work it out, the tension is equal to 0.50 newtons. Well, now that we know that, we can calculate what Tx is. Tx is nothing more than just the opposite of my angle theta, so it's T times sine. Right? T times sine of theta. Okay? So my Tx is equal to 0.5 times sine of 12. Right? So if you work that out, Tx comes out to 0.104 newtons. All right, now I think I have all the ingredients to figure out rest of this problem. Okay? So for part A, they're asking what is the speed of the mass? Well, they want to know what v is. So for part A, say we look in the x direction now, or the radial direction, okay? So sum of all forces in the radial direction is equal to m AC. Therefore, sum of all forces in the radial direction, well, how many forces are there in the radial direction? I only see one, which is Tx. Okay? So here, MAC is equal to Tx, which is positive direction because it is pointing along the AC direction, right? So mv squared over r is equal to Tx, which is 0.104. So my v is equal to r times, what's my r? 0.25 times 0.104 divided by mass of 0.050. Square root it. So my v is equal to, I get something like 0.722 meters per second. So that's my A. What about B? B, what is the acceleration of the mass? Well, that's easy, right? Acceleration is AC, and AC is equal to v squared over r. And v squared is 0.722 squared divided by r, which is 0.25. So if you work that out, your AC is equal to 2.09 meters per second squared. And that's, of course, radially inward, right? Radially inward. And then for part C, they ask, what is the tension on the string? I thought we already figured that out. So that's part C right there. We already did C. Okay. So I guess we have to do part C first before we actually do A and B. All right. Any questions? All right. Let's take a look at the next problem. All right, here, a mass M on a frictionless table is attached to a hanging mass of big capital M by a cord through a hole in a table. All right. Find the speed with which small m must move for big M to stay at rest. So this big M, if I were to just let go, this thing is going to pull it straight down and it's going to go like that. However, if I spin this thing in a circular motion, because of the momentum or inertia of this wants to go tangentially, it wants to always go out of the circle, right? Therefore, it's going to pull out relative to this mass, which will create a tension going in that inward direction. That tension has to be same as the weight of this big mass to stay at equilibrium. All right? So if I were to look at this big mass right here, this big mass is Fg, and this Fg is just big M times G. Well, that big mass is supported by this tension T. Okay, so I'm going to consider up direction positive. Now, of course, this thing is not moving, it's stable. So, sum of all forces in the y direction is equal to, right, ma. But acceleration for that big mass is 0, right? And sum of all forces in the y direction for the big mass is equal to, well, it looks like I have tension and I have Fg. So 0 is equal to tension pointing up, which is positive, Fg pointing down, which is negative. So my tension is equal to big mg. So that's obvious, right? So now if I take a look at this hockey puck right here, or this big mass, or small mass I should say, right? This will have F normal going straight up, and they would also have Fg going straight down of the small, right, m. And it would also have tension going in towards the center of the circle. And this tension and this tension are the same tensions. Okay, that's why I drew them purple. So if I were to take a look at this small mass, sum of all forces in the radial direction is equal to MAC. And sum of all forces in the radial direction is equal to, I just see tension. Right? Tension is the only one. So MAC is equal to, well, tension is in the same direction as my AC, therefore it stays positive. So mv squared over r is equal to mg. This tension is big mg. So my v is equal to square root of, right, mg r over small m. Okay. Alrighty. I guess next. Here, a small coin is placed on a flat horizontal turntable. The turntable is observed to make 3 revolutions in 3.14 seconds. Okay, what is that? This 3 revolutions in 3.14 seconds sounds like my frequency. Frequency is revolutions per second. So it makes 3 revolutions in 3.14 seconds. So if that's true, my frequency happens to be 0.955 revolutions per second. The radius of this r happens to be 0.05 centimeters, and that is 0.05 meters. Okay. So, let's take a look at part A. Part A asks, what is the speed of the coin, right, when it's riding without slipping at distance of 5 centimeters from the center of the turntable? Okay, so for part A, speed v is equal to, of course, distance divided by time. Distance is 2 pi r. Divide that by time to go around is called period. But we know period is 1 over frequency, and frequency is 1 over period, right? So this is same as 2 pi r f. So v is equal to then 2 times pi times r 0.05 times frequency. We already calculated that to be 0.955 revolutions per second, and it comes out to 0.3 meters per second. Okay. Then it asks, what is the acceleration, right? The magnitude and direction. So for part B, acceleration is just AC, really, right? And AC is equal to v squared divided by r. Therefore, v, which is 0.3 squared divided by the radius, which is 0.05, and what does that come out to? It should, so 0.3 squared, divide that by 0.05, get 1.8 meters per second squared. And of course, the direction would be radially inward, right? Towards the center of the circle. Okay. Part C. What is the magnitude of the frictional force acting on the coin if the coin has mass of 2 grams? So we know the mass now. The mass is equal to 2 grams or 0.002 kilograms, right? And for part C, they're asking, right, what is the magnitude of frictional force? Well, we know sum of all forces radial is equal to MAC. Right? And there's only one force, and that is frictional force acting radially to make it stay in a circular path. And we know this is F normal, and this is FG. Right? So here, sum of all force radial is equal to just F friction. Okay? Well, we know F normal, right? I'm not going to go through the whole steps, but F normal is equal to Fg, which is equal to mg. Okay? If you don't see that, let me know. We can meet after school and we'll talk about that. All right? So MAC is equal to frictional force. And since they want to know what the frictional force is, we just have to figure out what this MAC is. Now, since frictional force and AC are in the same direction, they're both positives. That is mv squared over r. So my frictional force has magnitude of 0.002 kilograms times, right? Now you can use V here, or you could just multiply that by this A and you get the same answer. So 0.3 squared over R, which is 0.05. Right? So if you work that out, I think you'll get, what do you get? Times, I guess you get 0.0036 newtons, okay? Or simply, my frictional force is equal to 3.6 times 10 to the negative third newtons. Okay? And then for part D, they ask, what is the coefficient of static friction? Well, we know for part D, our frictional force is equal to mu times the F normal, right? So since we already know what frictional force is, which is 3.6 times 10 to the negative third, is equal to mu times F normal is just mg, right? Which is 0.002 times 9.8. So what is mu? So mu is equal to, right? So I get something like 0.18367, so 4 as my mu. And that is mu sub s, by the way, because it is a static coefficient of friction. All right. Then for part, oh wait, this is when R is equal to, this is when R is equal to 0. I guess 0.05 meters. So that's not really D, sorry. D prime. D prime. They want to know when it's 10 centimeters away. So my R is actually 0.10 meters. In that case, things are different here. Why? My speed is different. So my V prime would be, right, 2 pi R prime F. Frequency doesn't change, but my radius does. If my radius changes, my V changes. Okay? Therefore, my V prime is equal to 2 pi times 0.1 times 0.955. Okay? So what is that? That is equal to I get 0.60 as my V prime, meters per second. Okay? And so, if I were to calculate, right, what mu is, here, if I were to calculate this frictional force was basically mv squared over r, right? So here, mv prime squared over r is equal to mu times F normal, which is pretty much that. Therefore, my mu is equal to, right, here, V prime squared over R, and this is equal to mu times mg. So my mass would cancel out, and I would have g at the bottom. Therefore, the mu is equal to now v prime, which is 0.60 squared. Divide that by r is now 0.1 times 9.8. So if you work that out, I think you'll get double this. All right. So squared divided by 0.98. Yeah, and I get 0.3674 as my mu sub. So when you're further out from the center of the circle, you're going to need greater friction to get that thing stayed in the circular path. All right. All right. So you could compare actually, right? 5 centimeter versus 10 centimeters. You can see that you're going to need greater friction when you're further out of the circle. All right. All right. Moving on. All right, so here, this is very similar to the note packet that we did, right? So let's take a look at what happens when things are going in a vertical circular motion, right? So a stone is tied to the end of the string, all right, and is whirled around in a vertical circle with radius r. Find the critical speed below which the string would slack at the highest point, okay? So here, if I were to look at the bottom of this vertical circular motion, here I would have Fg going down this way, and I would have tension going like this, okay? They don't necessarily have to be same size, by the way, right? Here, my tension is actually going this way, but my Fg is going down this way, so this doesn't really contribute to my circular motion at all at this location. Here, it hinders it. Here, my Fg is down, which is actually helping my object stay in a circular path. And the tension, obviously, is also in towards the center, okay? Now, I could make this tension longer, I guess, but here, if I were to look at this part right here, at A, okay, at A, sum of all forces, right, in the radial direction is equal to, okay, MAC. Sum of all forces in the radial direction is equal to, I have tension and I have Fg. So MAC is equal to, in this case, at the bottom at point A, in towards the center is the positive direction, so my tension stays positive, but my Fg becomes negative because it's going out of the circle. Okay? So mv squared over r is equal to, right, tension minus mg. So tension, in this case, is equal to, right, mv squared over r plus mg. Okay? Well, what about at B? At B, we're just going to have tension is equal to mv squared over r because FG is not in the radial direction. So that's easy, right? So at B, right, I just have tension is equal to mv squared over r because it doesn't really have any other force other than just tension as my radial direction because Fg doesn't contribute or hurt, right? Now what about at the peak, the highest point, at C? Here, sum of all forces radially is equal to MAC, right? And there are two forces again. And again, in towards the center will be positive direction. So F radial is equal to, there's tension, and there's Fg. So here, MAC is equal to, tension is positive because it's pointing in towards, plus Fg because Fg is also pointing towards the center of the circle. So they're both positives. So if I solve for tension here now, right, my tension here is equal to, right, mv squared over r minus mg. Okay? So, what happens when string would become slack? Right? This happens when tension goes to 0. Therefore, this, when tension goes to 0, the slack happens. So 0 is equal to mv squared over r minus mg. So v squared over r is equal to mg. And notice how the masses will cancel out nicely. So my v is equal to square root of rg. Okay? So, any questions so far? All right, good. All right, then. Let's take a look at the next problem. Here, as shown in figure 6-42, 1.34 kilogram ball is connected by means of two massless strings to a vertical rotating rod. All right. The strings are tied to the rod. The strings are taut, basically. All right. So there's no slack in it whatsoever for both of them. And form two sides of equilateral triangle. So equilateral triangle, all sides are equal. The tension in the upper string is 35 newtons. So this tension here is 35 newtons. Okay. A, draw the free body diagram for the ball. All right. So let's do A right here. I mean, since this is already started for us. So for part A, draw free body diagram. So I'm going to say that this tension, top tension, is here like so. Now this tension, I'm going to call that T1. Okay. And this T1 will have the horizontal component of T1x and the vertical component of T1y. Since it's equilateral triangle, these are 60 degrees, 60 degrees, and 60 degrees. And because they're 60 degrees, I can split this 60 into 30, 30. So this here will be 30 degrees. And obviously there's going to be FG, right? There's going to be FG. Right? Which is equal to mg. And this radius, right? Because this thing is radius, is going to be calculated as, oops, sorry, slipped. So here is 1.70 meters, and this angle here is 30 degrees. So this radius here is equal to, right, 1.7 times cosine of 30 degrees. So the radius of the circular path happens to be 1.47 meters. This is good to know because you're going to need radius. And if I were to take a look at the second tension will be here. I'm going to draw it away from that little line here. And this tension, I'm going to call that tension 2. This tension 2 will have its horizontal component and its vertical component. So this is T2x and this is T2y. And of course, this angle here is also 30 degrees. Okay? So we could calculate a lot of things actually, but I don't know if we should, but we could calculate the FG obviously, so which is 1.34 times 9.8. And our FG, if we do that, I think it comes out to 13.132 newtons. We know T1, which is, what is T1? 35 newtons. So most likely we can calculate, right, T1x and T1y. Right? So T1x is equal to T1 times cosine of 30. So T1x is equal to 35 times cosine of 30. And that comes out to 30.31 newtons for my T1x. And then T1y is equal to T1 sine of 30. So T1y is 35 sine 30. And that is half of that, 17.5. newtons. All right, that looks like, a lot of stuff. We cannot figure out the T2 yet, but that's what they want us to figure out next. All right, then, let's do that. Let's do part B. Part B asks, what is the tension in the lower string? All right, well, we know vertically we have this figured out, we have this figured out, and this is the only one we don't know. So if we work vertically, I think it may work out. So let's take a look at y direction. If we look at the y direction, sum of all forces in y is equal to m-a-y. And of course, this ball is not accelerating in vertical direction at all, so we know ay is 0. And sum of all forces in y direction for that ball, I have 1, 2, 3 forces, right? I have T1y plus T2y, right, plus Fg. So we know 0 is equal to T1y, we're going to keep that positive. T2y, we're going to make that negative, right? And Fg is negative. So if we solve for T2y, so T2y is equal to T1y minus Fg. So T2y is equal to 17.5 minus 13.132. So T2y comes out to, I get 4.368 newtons. Now I know somebody's going to ask me, well, shouldn't that come out negative? And the answer is, we already gave the sign negative here already. So we should get a positive value because we already gave the direction. So once we know that T2y, we know, right, T2y is also equal to T2 times sine of theta, right? So T2 is equal to T2y over sine of theta. That is 4.368 divided by sine of 30. And that should come out to double that, which is 8.736 newtons. That's my T2. All right. And now, part C. What is the net force on the ball at an instant shown? Well, the net force, obviously, vertically is 0, right? That's kind of obvious. So for part C, right, the net force in y is 0. We already established that right here. But what about the net force radially? Well, we know that is equal to MAC, right? But what is the net force radially? Well, how many forces are there? I see two forces, T1x and T2x. Those are the only two forces acting radially, and they're both pretty much going in the same direction, and they're both going in the same direction as AC. So T1x plus T2x are the only two forces. Right? So if I were to give directions, now obviously we're looking for this, right? So MAC, right? That is the net force in the radial direction, is equal to Tx positive, T1x is positive, plus T2x is also positive. So my radial net force is equal to, we already know what Tx is, right? T1x is, and that is 30.31 plus T2x is simply T2 times cosine of 30, right? Which is 8.736 times cosine of 30. So my net force radial is equal to, right, 37.9 newtons, right? Of course, the direction is radially inward. And that's the only force in net force-wise. So this is the total net force. This is also the total net force. I should say total. This net is redundant, so I guess this should be total. All right. What about part D? What is the speed of the ball? Okay, well, now I guess we could set that equal to MAC, right? So here, the net force radial is equal to MAC. And we know that is 37.9 is equal to mass, which is 1.34 times v squared over r, which is 1.47, right? And the r came from right here. Okay, so here mv squared over r. So if you solve for v now, my v is equal to, right, 37.9 times 1.47, divide that by 1.34, square root it. So that comes out to 6.45 meters per second. All right. All right. I think that's it. All right. All right, Jeffrey, I got you. All right. Any questions? All right. That's good. I think that concludes the circular motion, but we did not still finish the banked curve. Okay, so that's kind of something that we should be able to do later, hopefully after Thanksgiving, because I'm not going to rush that through right now and shove it down your throat. So hopefully you guys can work on that on your own over the Thanksgiving break, and then maybe I'll give you like a mock quiz or something you could work on during Thanksgiving if you feel like it. Just check the Schoology post once in a while. So, all right, here we go. I think most of you know about the multiple choice pretty well, and I think I'm not going to worry too much about it. However, this number 3, so many people got this one wrong, like previous years. So I'm going to actually do this problem. It looks like it's a straightforward thing, it looks like, but people actually really choked on this. So if I were to actually apply a force push horizontally on an inclined plane, you have to remember that you have to rotate your axis, so your x-axis is actually horizontal to your right, This is your x-axis, and this is your y-axis. Right? You have to keep that in mind. Right? So if I were to take a look at this on an incline for free body diagram, right? You have to think about all the forces acting on this x-axis and y-axis. Okay? So let's take a look at what's going on. So here, I'm going to redraw my box right here. Redraw this because this is dark and you can't really see all the... Okay. I'm going to draw this free body diagram. I lost my vertical. Oh, okay. So here is my box. You know, obviously, we have FG going straight down. Okay. This FG goes straight down. And you know, obviously, here is your x-axis. Right? This is your x-axis. And this is your y-axis. And this FG will have its FGX and FGY, right? So here's your FGY and here's your FGX. This angle here is 27 degrees. Now you have your F normal and you could see that I drew my F normal a lot bigger than my FGY here for a reason. Because this F push, which is acting in this direction horizontally, right? This F push will have F push X and F push Y along the rotated axis. And this is F push. And this angle is 27 degrees. And of course, we have friction acting in the opposite direction of motion, which is down the incline. All right? So we have FGX, friction, F push X in the X direction. We have F normal, FGY, and F push Y acting in the Y axis. Okay? So to figure out what the normal force is, okay, let's think about what the normal force is. So sum of all forces in the Y direction is equal to MAY. Of course, AY is 0 because this box is not going to be levitating off. So this whole thing goes to 0. And sum of all forces in Y, there are 3 forces. I have F normal, I have plus F push y plus FGY. So 0 is equal to F normal, I'm going to consider that positive. FPY, I'm going to consider that negative because it's pointing down. FGY is also pointing down, so I'm going to consider that negative. Okay, so I'm going to consider this direction to be positive. And I will also consider this direction, up the incline, to be positive. So my F normal, in our case, is equal to, right, positive FPY plus FGY. But what is FPY? FPY is FP sine of 27, right? And FGY obviously is FG cosine of 27. So you can actually calculate your normal force now, right? F normal is equal to FPY is 250 times sine of 27 plus FG is 29 times 9.8. So many people forgot this 9.8 times cosine of 27 degrees. So if you work this out properly, your F normal comes out to 366.7 newtons. Right there, you could tell that this is the correct answer because nothing else comes close to it. Right? But let's see if this is true. 0.26. Now let's take a look at sum of all forces in the x direction, right? So sum of all forces in the x direction is equal to max. But it is climbing at a constant speed. That means my ax is equal to 0. So if this goes to 0, this whole term goes to 0. So sum of all my forces in the x direction, how many forces are there? Well, I have px, right? I have fgx, and I have friction, right? So here, fpx plus fgx plus f friction. Now let's give directions to all this. So 0 is equal to fpx. I'm going to consider that positive. So fpx is positive. Fgx, negative. Friction, negative. So since I'm calculating for friction, let's isolate to the other side of the equal sign. So my frictional force now is equal to, right, fpx minus fgx. Well, my friction is mu times F normal, right? That is equal to Fp cosine, right, theta minus mg sine theta. So my mu is equal to 250 cosine of 27 degrees minus 29 times 9.8 times sine of 27 degrees. The whole thing divided by F normal of 366.7. So if you work that out using your electronic abacus, you should get 0.26 as your coefficient of kinetic friction. All right. Any questions? So this is a good problem, okay? This is a good problem. A lot of people got this one wrong. All right. Yeah, I'm going to end the lecture here. What I'll do is I'll put some. Nah, you know what? Enjoy your Thanksgiving. I'm not gonna rush you. Just relax, enjoy. No homework. But if you can, you should have completed your embankment problems previous to the ones we did, right? So we'll go over that after Thanksgiving, and then I'll give you assessment on that stuff all together after Thanksgiving. So enjoy your break. All right? I'll stop the recording here.